So, let's have a look at that, right. So, putting into PML, okay. So, in PML what we started writing the Maxwell's equations in terms of del H to give that coordinate stretching number, right. So, that I wrote was equal to j omega epsilon E, okay. There is no current term over here, and further let us just make it epsilon naught, because we had discussed previously that between the interface, I mean at the interface between vacuum and PML, epsilon mu were the same, right. So, now I am talking about the PML region where I am going to write this Maxwell's equation. So, now let us just take one of these terms, okay. So, for example, we can take the ESZ term, let us just look at that. So, what is that going to be equal to? When I look at this side, okay. So, this is the equation and I want to look at this term, okay. So, what should I write over here? There is going to be obviously del by del Z, Z cross H, anything else? Exactly, 1 by SZ, that is the left hand side, okay. So, I am only taking the third component, right. So, only third component. You can take all, but I am just simplifying it right now. And what happens to the right hand side? J omega epsilon naught E, ESZ, correct, okay. Like this there is a 1-to-1 between all three. So, if you want we can, if you want we can write it all down, should I? It's understood, right, for each and so on for each component, right. This is what PML is telling us, and seemingly unrelated, this is what a lossy medium looks like. So, is there a similarity or something that we can use? Okay, so this is for, let us just write it, this is for PML, okay. Let us write down for lossy. Lossy medium has no relation so far with PML, right. So, let us just write down what the lossy medium says for us. So, it says that del by del Z, Z cross H was equal to j omega epsilon naught epsilon r minus j sigma by omega epsilon naught E S Z, right. This is, I am just rewriting this equation number 3. See a few blank faces, is it clear what I did? So, let us take one step back, lossy, so Maxwell's equation were rewritten in this, no problem. From here I wrote it in terms of 3 vectors 1, 2, 3. Now, for example, I look at the third component, right. So, this term over here, those 3 may or may not be orthogonal, I mean they should be orthogonal, I should say, yeah, fine, because these x hat, y hat, z hat are orthogonal. So, x hat cross some same vector, all 3 I will just get another set of orthogonal vectors. Now, I am looking at the third component. So, the third component is being written over here, this equation over here, right. That is what I have written over here. This is the third component, which is on both sides I have the third component, okay. So, now we have them both on the same page. So, this is for lossy media and this is for PML, and what we want to do is compare these two characters. So, looking at this, what SZ is the only thing that I have to set, right. In when we did our PML, if you go back to the summary of PML, medium 1 was all the parameters 1, 1, 1, 1, 1, 1. PML was all of them were 1 except for the Z parts. Here I called them S2 and S2. And they were both equal, and the discussion had ended by saying there should be some S2. What should that S2 be? It should be complex, but we had not decided what that value is, right. So, when we come down to implementing, we have to say what is the value of that S, right. So, after looking at the comparison with lossy media, we find out that the interpretation of Sz can be taken from that of a lossy media. It's as though, so if I had a lossy media where I set this epsilon r and sigma, I get the value of Sz, right. So, I can write down Sz is equal to epsilon r minus j sigma omega epsilon naught. And remember, that is what I wanted for a PML medium. I needed a lossy thing so that the wave decays inside, right. That is what we saw over here. For time convention e to the j omega t, I needed S is p minus jq, right. So, that is what I get to set over here. It is like p minus j times q, but the parameters in our hand are epsilon r and sigma. We can decide what those numbers are, okay. So, this is, so in terms of implementation, why did I sort of take recourse to lossy media? Because we already know how to implement lossy media in FDTD, isn't it? We have discussed that. I will write down the update equation again if it is not clear, but we already know how to implement lossy media, therefore, we already know how to implement PML. Yeah, but if I make, so remember this coordinate stretching is a way of understanding PML. So, we have understood PML and we have understood that PML is the same as lossy media, but remember that this is Sz only, right. It's anisotropic. It's not going to experience the same loss. For example, Sx and Sy. What are the values of Sx and Sy? 1, right. So, that is not a purely lossy media, right. So, that's the difference. Let me write it over here. Sx is equal to 1, Sy is equal to 1. If all of these guys were the same, then I am right. And remember, what I have written here is only for the z component. When I look at the d by dx term, what will I get over there? Sx will be there, which is 1. So, that interpretation is not of a lossy media, right. So, we already know how to implement this, So, but I just rewrite it over here. Our update equations for H, for example, were right, curl of H is dd by dt plus j. J I am writing as sigma e and d I am writing as epsilon e. It is inaccurate, but we will live with that. What are the time indices? We had said that electric field is every integer time index and magnetic field every half integer, right. So, this is n minus half, therefore, this is also n minus half and this is also n minus half, right. And the problem was, of course, that with this term over here, I am not storing electric field at half time integer instances. So, in terms of implementation, this became E n minus E n minus 1 by delta t, no problem. The second term, because I am not storing electric field at half integer time instance, this became a average, right. So, this became E n plus E n minus 1 by 2, right. So, we know how to implement this equation, right. So, when I take the component wise which part is Sx, which part is Sy, which part is Sz, I know how to implement this, okay. So, I am not going to write down those very detailed equations, but you know the principle now. I have to set these S parameters and I get my PML, okay. One final sort of and very important take is, yeah, why do not you tell me? So, I mean, so sigma is here and this epsilon is what? Epsilon ER, right. So, here is your epsilon r, here is your sigma and that is your Sz. So, you get to implement your S parameters over here. It automatically, you just have to implement the correct components, do not do it for all x, y and z, otherwise you will be in trouble, okay. But remember this S, when I said Sz over here, right. So, let us go back to this equation over here. This was if I wanted to decay a wave in the z direction, right, this was the z direction over here, I chose a SZ to be different from 1, correct. So, if I want to absorb a layer that is going into the Z direction, I choose SZ equal to whatever, Sx Sy equal to 1, right. Those are the parameters that we had chosen over here, correct. Now, let us look at a realistic 2D computational domain. I am exaggerating the PML thickness, okay. So, this whole thing is PML and this is my computational domain, my object, okay. I am purposely showing it very big, and let us make our coordinate axis like this, x, y, okay. So, this in practice what happens is, you break up this there are these many distinct regions of the PML. What is distinct about them? So, for example, this part over here, what all should be, in what direction should it absorb the wave? X. So, what will be non-zero over here? Sx, right. So, the parameters for this part will be Sx 1, 1, right, make sense. What about this part over here, the left part, again Sx, same direction, Sx 1, 1. What about this guy over here, 1 Sy 1, 1 Sy 1, that leaves out the corners. What should the corners be? Sx Sy 1, right. So, the corners are slightly different because I want to absorb it in, I mean it is a wave that needs to be absorbed in arbitrary direction. In the corner regions. If I have a 3D thing, then in the corners I will have Sx, Sy, Sz. Yeah, but the loss, yeah, it will be exactly like a lossy media, yeah. But for example, the intermediate ones, they will not be purely lossy media, they will be anisotropic. For example, here. No, so this PML is not for normal incidence, this is going to absorb any wave that is incident on it. No, so this interpretation that we had over here, this is absorbing at all angles that are incident on this interface. But I mean the axis of the PML is defined by Z, so a wave can come at any angle. So for this guy over here, the parameters were 1, 1 Sz, but this absorbed a wave incident at any angle on the Z interface. It need not be travelling along the Z, but the absorption, I mean the parameter that I have to set is only the Z parameter, but it is absorbing any direction incident on it. The wave is travelling in any direction, no, the wave is travelling, is incident on it in any direction, that is what we showed, this reflection coefficient that we had, this r over here and this r over here, this was 0 regardless of which angle the wave came at, right, you agree. The only parameter that I had to set over here was the Z parameter. This does not mean that the wave is travelling only along the Z direction, the wave is incident at any angle, but the parameter that I need to set is the Z parameter. You should not interpret this as the wave is only travelling along the Z direction. The absorption is going to happen along this, it is an exponential decay along the Z direction. Yeah. So, let me draw what you are saying. So, you are saying, let us say I have an interface like this is my Z axis, let us say. Now, a wave comes at it at some angle, right, and what we find from this formulation is this r is equal to 0. Yeah, and I have said this is 1, 1, 1, this is 1, 1 Sz on what? On another interface. So, let us take another interface here. What differentiates? Okay, so the question is, I have interface I1 and interface I2. I2 has coordinates 1 Sy 1, right. So, in I1 I had 1, 1 Sz, in I2 I had 1 Sy 1. So, what differentiates? Right. So, if you look at the way we derived this, for example, when you look at the reflection coefficient over here, when I assume that the boundary was over along the z equal to 0, I got k1z, k2z. That is why I needed to set sz. But when I come to an interface like this, I will not get k1z and k2z, I will get k1y and k2y. That is why I need to set sy. And then it is able to absorb any wave coming at it. That is making the reflection coefficient 0, but the wave is travelling at any angle, it does not matter. The trouble is, I mean the interesting thing is happening at this corner region over here, right. So, corner region over here, where will it get the wave from? The wave that has entered the PML and not yet fully absorbed, but travelling at some angle, right. So, for example, something like this, it is entered, not fully absorbed, and then it enters over here. Okay. So, it is a more cumbersome derivation, but you can take it in the plane. The k vector is in the plane in the 2D case, k vector is in the plane. The electric field polarization can be anywhere, does not matter, but k is in the plane, that is what makes it a 2D. Okay. So, this is where I mean implementation wise, here the bookkeeping is a little bit more tedious, because you have to keep track of x, y, z separately and these parameters sx, sy, sz separately for each thing over here. Okay. And I think the final thing I can say, for example, if this is L over here, a typical way of implementing this S parameter, right now our interpretation is that Sz is like this, sorry, Sz is like this. But what is usually done in practice is, so by the way, this epsilon r can just be made 1, right, because it is adjacent to vacuum, epsilon was same on both sides, so this is 1. So, typically what you would do is that sigma you would make a function of x, and you would do something like x by L to some power m, okay, and this is 0 less than x less than L. So, the loss increases as it does not become suddenly lossy, it increases as some polynomial power of x. This is a implementation issue, this is what gives the best performance. Theoretically you do not need this, but when you get down to implementation, this is what gives the best performance. Some lossy medium, yeah. In terms of implementation, it is a kind of a lossy Sz, yeah, that is it. But I have to rewrite my Maxwell's update equations to get that Sx, Sy, Sz parameters inside. That is all you have to do, and then set the correct values. And this can be done and is done in FEM also. Right. Okay, so that brings us to an end of the discussion on PML.